We have started. Hello, YouTube. Hello, everybody. Hello, Ben. How are you today?
I'm very well, thank you. How are you, Bill? It's good to see you.
Flustered. I got too many screens open, but we'll work our way through it here. We've got an exciting topic today. We're going
We
to
do.
talk about programmable logic devices, PLDs, specifically the one we call PALs, programmable array logic, as
Yeah.
opposed to PLAs, programmable logic arrays.
Now these
And
are I've always loved this topic, and it takes me back to 1995 in my digital electronics 3 class. The two big juicy topics we covered were programmable logic and digital signal processing, and I
right,
loved
right.
them both. And there were other topics besides, like yeah, we also talked about how electronic displays worked, and back then it was all CRTs still. So we talked about the flying dot and how to
Right.
make a display, and even then, PALs were sometimes some of the models that had been used extensively in electronics, even by the mid '90s, were starting to get hard to get the silicon. But look at this, we're still
We
doing
found
it.
some.
And
Yeah.
what I love about this, I'm glad you picked this. I got super excited when you brought this up because you can't you can't easily begin to understand FPGAs and modern CPLDs, complex PLDs, without having some kind of background in these PALs and GALs that we used, which you can still get.
Right.
Like, I didn't
Right.
realize you mentioned this and sent me some links, and I'm looking it up. I'm going, far out. These chips are still active. They're active, and they're cheap. That's awesome
Right.
because they're super useful and they're
And
fast.
and they are. And what a PLD does for us is it's a small programmable part. And for example, the example I'm going to use here today is I've got a 6502 small board computer I built for something. And I've been talking with Frank Buss in the Discord chat. And if you want the Discord invite, go to Coriolis-effect.com and join our Discord channel. But I'm going to get Frank to do the software code to hook a vacuum fluorescent display to the 6502. Matter of fact, that same vacuum fluorescent display that we've shown in the past here. But there's always in a small computer, there's one function that a PLD just screams to be put in, and that is the address decode, right?
Yeah, yeah,
An address decode quite simply looks at the address coming out of the processor
which
and
is a
looks at the
binary number.
right,
It's an integer, unsigned, right?
right, which I visualize as hex. We almost always knock it into hex then. So we'll
Yep,
say
because
something
each
like,
digit is
go ahead.
each digit is a nibble
Right,
for hex. So
right.
it's neat and tidy. Yeah.
So, for example, we might have a ROM that starts at F000 in the 6502. It has to be up high because that's where the reset vector is. And then down low at 0, we have RAM usually. But somewhere in there, we have to stick our I/O.
Yeah.
Well, if you try and do that with and OR gates and LS138s and LS139s, you end up with a small jungle of parts to do it. And guess what? There's usually some glitches in there too, even though
Yeah.
most people don't see them.
Well, you're adding more chips, more lead frames, more PCB routing,
More delays.
more capacitance,
Yeah.
and more inductance to the whole system. And so it might be fine for a 2 megahertz thing, but so what we're really talking about here is you can shrink what would be up to 5 chips down to one
And have one
and
level of
speed
delay.
everything up. Yeah,
Right. Instead of having this path goes through 3 AND gates and an OR gate, and this one just goes through the OR gate, and you end up with the terms racing each other. Going through the PAL allows me to do all kinds of logic and yet still have the same delay going through it. So, matter of fact, if we, let me see if I can expand a data sheet here and show this is a logic array.
Yep. So
where
those are,
where the go ahead.
So each one of those input ports with a number is a pin, or is that a pin number on the actual chip?
Yes.
Right. So those are your inputs on one side of the device, and you've got outputs on the other side. So it's super easy to do PCB layout for these.
Right.
Everything goes in one side, out the other. Right.
And as soon as it comes in the chip, the very first thing we do is we see, it's hard to see here, but this makes an inverted term and a non-inverted term and puts it into the array.
Yeah.
And this is an array of AND terms that get OR together here at the end.
Right.
So
that,
we can
that
say
crisscross matrix in the data sheet is you could think of it almost like where two lines cross.
right.
The way that PALs used to work, the one-time programmable devices, each of those were linked, and the programmer, the EPROM programmer that could program a PAL, would blow the fuse. So you would disconnect the ones that you didn't want to be connected. And most of them would be blown, except for just the few that you needed for your logic. And they form from the buffer. You've got an input true and an input complement. Like you're saying, there's an inverter or it's a differential drive.
Right.
So you can take an input, or you can take an input barred. So you can get whatever you want. True or complement, and wire and those together, or wire or it's basically a sum of products, right? Is that what you call it, Bill?
Yes. Yeah, that's what I would call it. And also, I'll say that this family is different. We used to use this as a PAL, which is an AND OR array. You do the AND function first in the ORs. We used to do PLAs also, which were OR AND arrays. But this little part here, like you said, almost preceded FPGAs. My memory is they came out at the same time as the old Xilinx parts. And the Xilinx was basically a big PLD. It had 64 cells in it that basically had 5 terms each, whereas you actually had more terms available, per cell in the PLDs that we're showing here today.
So zoom into that data sheet again. Show us what's at the end of that, because it seems like for each input and for each output, it seems like it's grouped into chunks, basically.
Yeah,
so
let me see if.
Yeah, so on that big matrix part,
there's a matrix.
Output logic is this block, which I guess the data sheet gets into more detail after that. But the cool thing about that is, I see for each input, it's like there's this whole section with an output block. All the wire or array with the AND at the end, or the product terms that they're called, and then there's something in that box and feedback that comes back. So if you have feedback, it means that feedback can also be linked to the next group down, right?
Right. And so here's just a little, here's a blowout. Now, this is the old L8. So there were 2 versions back in the day. There was the L version, which meant an active output went low, and they were immensely useful for chip selects. And then the V's came along, and they have a flip-flop. We're not going to be talking about them as much today unless I can find the data sheet real quick. But here's that feedback term you're talking about right here. This feeds back into the array, and you make flip-flops, you can make latches, you can create state machines out of this simple logic.
Yeah, well, that's the output logic there can be configured to include or not include a register. See, there's a clock input on those as well. And so the point about the V, that's it. So the point about these V.
Whoop, I lost you. So Ben was talking about the V being versatile and a versatile block, which means it includes this flip-flop right here. and a clock. So then we can really do our different kinds of state machines. There's a kind where you do the logic in front of the flip-flop, and a kind that includes the flip-flop and logic, Mealy and Moore machine, something like that. My memory's too old. Okay, you're coming back. I was just explaining the V, so go ahead.
So why is it always 11? It's always 11 minutes
11:10.
I don't know what you said. I don't want to repeat what you said in case, but basically, these V devices mean versatile. So they can act as an L, PAL L, a GAL. GALs were the ones that first introduced generic array logic. They were the first ones to introduce the register, and you could build state machines with them. So they weren't just good for custom address decoding. You could even use them as a core of a whole program.
I've done a whole DRAM controller in a 22V10. I had a whole DRAM controller built into it with the state machines, including the refresh state machine, the state machine that says RAS falls now CAS falls, all of that in a single 22V10 part. And it was just wonderful.
Super clever. Yeah.
Yeah. And so here you might ask, what's this exclusive OR gate here for? And that's simply how we do the logic conversion. If that fuse is blown, it's not fuses anymore, but I'll say that. You can invert the whole thing with a term that's blown to be true. So, and we were looking at this sheet earlier. I keep thinking about the days when we used to actually circle in these dots. We would go into here and make dots.
Yeah,
to
you'd
show the logic.
You'd do your product terms on paper. That's how we did it when I was.
Yeah, I lost you again, but Frank in the Discord channels talking about now they include 18 by 18 multipliers. Yes, the FPGAs have a lot of dedicated stuff. So okay, you're back with us.
Yeah, I know. I was going to say it was GALs. So I said GALs introduced the registered and the ability to make state machines, but then things got complicated. Right?
Do you remember your Mealy from your Moore state machines? Do you remember which one's which?
Oh, don't put me on the spot like that. I do.
No, I don't remember. I'll tell you right offhand. I don't remember myself. I think Moore was the one we end up doing with these things. One includes the flip-flop in the output terms, and one is a step ahead of the other one, is the way I remember it.
Yeah, and it's also about the encoding, what encoding options there are for them.
Right.
So you can create a state machine. You can synthesize a state machine using something like a Johnson counter or a gray code encoding, which is a Johnson counter, where it's a row of flip-flops with a feedback loop, and it goes through a set number of states, and each state can then be decoded. And then the other kind is more. So that's like using a counter and a multiplexer almost.
Right.
And then the other kind is simpler and uses a bunch of flip-flops with feedback. So
and we should do a show on just state machines, because it's complex enough we can't talk about them here today easily. I would say
I'll have to do some research and find a nice state machine bubble tool that can, because I know the FPGA tools, a lot of them come with a state machine editor that lets you actually draw the bubbles and name them and specify what the state change criteria are and all that, and it's super powerful tool for logic synthesis in FPGAs. And we didn't have any of that with these. We had to do the Boolean logic on paper, and remember our Ducano mapping and all of that stuff on paper. Right. Come to the simplified product term, and then, as you were saying, circle the junctions in here, and then it's like hand assembling, it's like the days of hand assembling code, and then, but you're showing so that segues into how do you program this, because they got complicated and we needed a better way to program them.
Right.
And you can still get this software, right? You posted
Yeah,
on the
so
on Discord.
Philip from the Discord did mention that Moore has the logic before the register, which is what I was trying to say. And this architecture you see here does lend itself to more state machines because, as you see, it's the logic, and then the register comes afterwards. And somebody else mentioned that there were like 16R. What?
Yeah,
let me go back
that's
up.
right. That's right. And Mark says,
But the R,
there's
you had to use the register, whereas the V, you can choose whether you use the register or not.
Yep. And Mark's saying there's a free state machine tool that generates Verilog too. I'll check that out. Physm. Sounds good, Mark.
Okay.
Thanks.
Yeah. So the tool that's still around today, and I used to use Palasm back in the day.
Yep. I remember that one.
I have a copy of Palasm still in the box somewhere. And it's on 5 1/4-inch floppy, so it's completely useless. I don't know why I keep it around. But you can
find
get
it. You probably find it somewhere on the Internet Archives.
probably, yeah. So the program we do have, and I'll stop by saying the way I found that I could still do. Let me do this for a second. The way I found that I could still do PALs is I found a PLA still in DigiKey, and then worked backwards from there. So I started by saying, what can I get? And then how can I program it? So I ended up with WinCUPL, which you can get. I put the link to this in the Discord for the show. And you can still download it. It turns out Microchip bought Atmel, but Microchip still has a link to the download here. And this is my WinCUPL screen.
Yeah, I was just blown away. I did a part number search since you'd mentioned this too, just real quick, and it's easy, at least in small quantities. You can still get these parts really cheap. I'm impressed that they're not just held by some troll as a. You know, there are some electronics distributors that stock up on something that they know is going to go discontinued because people like the military have to still be able to buy it later on, and they'll pay premium to maintain product life. But these are actually still active parts, which is cool.
Oh, that's why I used one in my little circuit board here. I would not have used it if it was something I had to buy it through AliExpress only. I just simply wouldn't have done it. So it's by the way, we talk about the days from gals and stuff. This was the book I first learned about PLAs when it was called Monolithic Memories Incorporated, MMI. This is a book from 1986, and this was one of the Bibles.
Hold that up closer, because the color of the text on the front is hard to read.
Right.
PLE Device Programmable Logic Array Handbook.
Right.
Cool.
Right.
Check
and
out
it's got.
I'll probably look for that on Aid Books or something.
Yeah, and it's just chock full. I mean, the whole book is about this very topic, and there they show. You're talking about bubbles and state machines and whatnot.
They've got the traffic lights project.
The traffic light one, yeah. Well, let's talk about that a little bit. A traffic light may seem simple, but it's a great demo where you say, well, go to the green light, sit there for an event. And then where do I go next? Well, if I'm at the green light, I'm going to go to the yellow light next, and I'm going to sit there for a different amount of time, and then go to the red light. And so that's actually a state machine that's driving that, though it used to be relays and stuff.
Yeah, that's true. Yep, relays and timers. And that's a challenge I wanted to put out there one of these days is throw out the question, and I started thinking about this and feel pretty confident that there's a way, but throw out the question. Build a state machine using only a 40106.
That's a hex. That's a
hex inverter.
Hex inverter.
Trigger.
Right.
It's a hex inverter Schmidt trigger. So
CMOS.
Just a little design challenge. Throw it out there to the group. Who can build a state machine with more than let's raise the.
Am I allowed to short the outputs together using resistors?
Make a state machine out of a 40106 with more than 2 states.
Yeah, real important. More than on and off. Yes.
Yeah.
We need.
Yeah, not just an oscillator. It's got to be. So I know that there's ways of doing it, but you're
Right.
combining analog. Anyway, so what are you showing us here, Bill? This is what program is this for starters?
So this is WinCUPL, and it's as it sounds like, it's a Windows version of the couple that used to run under DOS. And we don't have DOS anymore, but we've got this program, and again, downloadable from the Microchip website. And the very first thing on here, let me go over here, is options, devices. Now, you can't see the screen that just came up.
No, I can't.
I'm going to make a new thing just to show you because this was important. Add source, screen capture, smart, boink. There we go. So
there it is. Yep.
This was the first part of the trail to get to being able to program it. Is I found that I could get an ATF 16V8B right here. I found that I could get that on DigiKey. And I could get it in a dip package, which like people like the 8-bit guy, they're doing a computer all-in dip. And it's like, well, who has dip these days? Guess what? Atmel or Microchip does, right?
Oh, Microchip will keep doing that for the foreseeable future. I spoke to some of the folks there a while back about this and saying that it's actually part of their marketing, and it makes perfect sense. People use Microchip parts because it's easy to prototype with them.
Yeah.
It makes a big difference. Yeah.
What that leads us to, though, is this mnemonic that I've just highlighted. This becomes a G16V8A generic part, which I would never have known that that's the key to this if I didn't trip into the screen where I do the selection here. Let me see if I can make the screen go away, because then we're going to find that gets inserted into the actual device, and that's real important. We're going to find.
So CUPL, I was just looking at a CUPL tutorial again from a university website. CUPL has these reserved words for specifying what's the part that it's compiling for, right?
Right.
And all of that's almost like that header or the comments at the top of your file, and they have to be there.
Yes. So I got to redo the screen capture because it screws up when I do the mini window like that. Give me a second.
It was doubling up on them.
It sure was. And it's back. So, yeah, anybody wants to produce this show so I'm not producing and talking at the same time, give us a shout. We'll figure out how to make it work. So somebody just said, hello, Mondo 8-bit said hello. Hello, Mondo 8-bit. So here we have my little tiny address decoder. And the very first thing we do is we define the pins. So I've got the clock from the 6502. Why do I have the clock? That tells me when the address lines and data lines are valid. Then I've got the address lines A15 to A8, which means I can decode those upper nibbles that you were talking about. And then I have the read-write line. I need the read-write line because I need to create a gated write. So this thing does both a chip select and a gated write signal. The reason for, let me pull this down for a second. This is important. The reason why I need a gated write is if you just let the write line go low while the address lines are changing, you're writing all kinds of places in your RAM. You need the address lines to set up and be stable and then strobe it. We call them strobes, actually.
Yes.
The write strobe says addresses are stable inside the RAM. The address decode won't be flipping around, ruining the memory contents everywhere. He goes, I'm already stable. You mean that cell right there? Go ahead and write to it as the write line goes low.
Yeah.
Now, at the end of the write strobe, at the end of the write strobe, the data is valid and has been valid for a period of time called a data setup, and it's held for a data hold time. So the strobe goes low when addresses are valid, and the strobe goes high when both addresses and data are valid on a write cycle.
Yeah. You could almost think of strobes in memory devices as the clocks, even though they're asynchronous, but for that reason. And we call them strobe because there's not a master clock that it all has to be synchronized to. So that's the difference between synchronous RAM and asynchronous RAM. But the strobes are still kind of a clock, and it's good to think of them that way, because then you're remembering about those setup and hold times.
Right, right,
Yeah,
right.
yeah,
So, and then I get to the outputs where I said, okay, I want to select RAM, but I've done one thing here, and I've stuck a exclamation point in here that says when, that means when the RAM select is true, it will be low. So I've set the polarity of the outputs with these different exclamation points.
yep.
Right? So then I come down to some intermediate terms. So basically I want to take these address lines and this logic, and I want to decide when these outputs go low, or whatever state, but I've defined them all as low. So the very first thing I did was I bunched up the I/O addresses. I took the addresses themselves and I made a value called I/O address. All right. So now in the future, the next term, I can refer to I/O address instead of A15 to A8. And I say, look, if it's from E1000 to E0FF, this equation's true.
Super easy.
Super easy. So here I've got the RAM address is at 0 to 7FF, or 32 kilobytes. The ROM is available 8000 FFF, which overlaps the I/O, but I'm going to show you that trick here in a second. And then I've got my I/O specified at E1000. Now, I can move this easily. I can move the I/O to C1000. I can move the I/O to 2000 doing this technique. So now we come down to the bottom, and for the ROM to be true, remember it'll be inverted, I say, okay, I don't want RAM to be true, I don't want I/O to be true, and I want it to be a read cycle. Right? So basically what I've done is I've said, hey, if it's not RAM or not I/O, be ROM. So that way there's no illegal state on a read. I've said if it's not one or the other, it's this. And so ROM is the master one.
Yeah.
And the RAM is actually way simpler. The RAM is, hey, if RAM equation's true, it's RAM. If I/O equation's true, it's I/O. And the read-write strobe says, well, okay, first off, we're only going to strobe it on a RAM. So we qualify with RAM.
Yep.
We're only going to qualify if the read-write line's low, and we're going to do that clock that we said, the phi, that says, okay, it's valid.
All right. So that's what you call a gated clock.
Yep.
Which means you're actually using an AND gate with a clock going into one pin and the read-write and RAM equation signals going to two other inputs to the AND gate, and then and only then will the output go low.
Right.
So that means the clock may be asynchronous to the right signal. So how do you deal with that timing? Because and this is totally cool in a PLD for basic address decoding, and as you said, you don't want the write enable to happen
right
at some
there's a tight timing condition in here that the PLD is uniquely qualified to address, and that is the data on a 6502 is only held for 10 nanoseconds. That's 1 LS delay.
Wow.
So if I've got to go through an AND gate and an OR gate in an LS family, I've blown the cycle. And everybody not everybody, but most people that come to me and say, help me with my 6502 design, first thing I do is I go in and say, I check that the write enable's going away within 10 nanoseconds after the clock ends. And if it doesn't, they're going to blow the read cycle. So with a PLD, I can take an AND and an OR and an AND and still get it done in one logic level delay time. Otherwise, you got to start using F parts, AS parts, or HCT, not HCT, ACT parts or something like that.
Yeah. Now, in an FPGA, you would generally tend to avoid gating clocks. Instead, what you use is you have the whole system is synchronized to a clock, and you have dedicated clock inputs and registers, which is where that's maybe the difference then too between the generic array logic features with a flip-flop at the end. You have a clock, and what you're doing then is you're using the flip-flop to carry your product term through.
You pipeline
at an exact moment in time.
Right. And so you start with a higher frequency clock, which is very key. If you want to do something at 1 megahertz, but you want to keep clocking your midterms, you start with a 16 megahertz clock or something. And you're absolutely right. Rather than have logic go through more logic and start to race, you go through a chunk of logic, flip-flop, chunk of logic, flip-flop, and it's called pipelining.
Yeah. Yeah, exactly.
So,
yeah. Cool.
All right. So I've redone my screen capture here so you can see some things here.
Compile? So WinCUPL has a couple compiler in it, right? Which I would hope that it's possible to drive it from command line as well. But
I don't know. Yeah,
I haven't tried it yet because this is just text files, and it'll generate a JetX standard output, I believe.
Right. Yes. So, and I'm disappointed here. You can't see, but when I go to run, I have 4 options, and you can't see it. I have device-dependent compile, device-independent compile, which means I can just compile the logic to check my logic, or I can compile my logic and make sure it fits in the part I've chosen.
Wow.
And then the other 2 are device-dependent simulate and device-independent simulate. I'm not set up to show the simulation here, but this simple little program from the old days, not only can you program a PLD, you can simulate it. It means you take the time to go, oh, here's the address range, 0 to Fs, and what are the outputs? When do the outputs change as you walk through those different values that are associated?
And to do that, you need
it's
to
called
set up
WinSim.
a test bench and all that. Yeah.
Right. We didn't call them test benches in the old day, but that's absolutely what it is. Yep. So what I'm going to do,
whatever. Yeah.
Yeah, a stim. So I'm going to do a device-dependent compile and see if you can see the results here.
I could see you clicking on the button.
Yeah. Oh, can you?
I guess it compiles almost instantly on it.
Yeah, it did. Whoops. I need to pull this up. You didn't see the. But yeah, it compiled almost instantly, and here's the results. It said, "Hey, you're good to go." So I've now compiled what normally I would have to hook lots of AND and OR gates to go E0 to E0FF. That's 1110. That's A15 and A14 and A13, but not A12. It's all done for me, and I got to do it in hex, right? So WinCUPL, cool. Nice, cool little program. If it's long in the tooth, acts like it's long in the tooth, but hey, it's still available and it's free.
It's well and truly debugged by now. It was fully debugged 20 years ago.
Right. All right, so let me try and it's not letting me, so I will just have to delete this screen because...
Right, but you're going to bring up the programming software and show us how
I am. I have to delete the... There we go.
There it is. So you've got the XGQ programmer. So this is the software that comes with the... What is it, a TL8662 Plus or whatever? The standard pair that you get. We all have one of those, I think.
Yep, let me... TL8662 Plus.
TL8662 Plus.
Now, I don't be... Oh, what'd I do with them? I had a whole box of... Ah. There are lookalikes, right? But this didn't work for me. For a long time, I couldn't do PLDs because this one, for example, is a... Oh, this is a TL866CS. I couldn't get it to do PLDs. Here's a G540. Couldn't get it to do PLDs.
Oh, really?
There is... Yeah, I couldn't. I couldn't find one that was available.
Oh, okay.
Yeah. But I couldn't find one that would do the ATF series that are still available from DigiKey. So somebody will go, oh, hey, my CS works. Mine didn't. I needed the 2 Plus to be able to do this. So here we have, so here's the board I was doing, and the PLD is this part right here. So this is a nice little board. I've got my processor. I've got my RAM. A 6522 goes here. I didn't realize it was missing, so it's a good thing I'm looking at this now. 6522 is an I/O chip, and the Chuck Peddle, the guy who did the 6502, says, well, the 6502 is fine. What really broke the industry open was the I/O chips, right? Because if you're doing a data terminal, you need something to read the keyboard. You need something to make the screen active. So just having a microprocessor and some RAM didn't work. By the way, the first RAM was shift registers. They needed an I/O part. And so he's kind of was really proud of his I/O devices. So that's all it's here is ROM, RAM, processor, and I/O all on a single board. And then I happen to have a little board here that is meant to plug into this that has a Teensy 3.5, which is 5-volt tolerant. And I was going to do an in-circuit emulator from here to here, but that's for a different day. So here's my board that I'm targeting. Here's my processor, or my programmer. So let me show you the programmer interface.
John, you're asking if there's any non-Windows alternatives for WinCUPL. That's a good question.
Well, if you can find CalASM, yeah.
I would imagine there's got to be something available on Linux by now, which means also Mac if you're using Mac. But even still, like WinCUPL, it's just a compiler, so it doesn't need hardware drivers or anything. I'd say it'll run.
Somebody could write this in Python in a day.
Totally. And I'd be surprised if there isn't already some website out there where you just upload it and it does it. But right. I haven't looked.
So let me get my glasses on here.
So the other thing we used PALs for consistently back in the day was decoding 7-segment displays. That's one of the most common.
Oh, yeah. And again, you can't see the screen I just opened, but I did a file open and I loaded the JEDEC file, the .jed. Okay. That was the output from WinCUPL. And so now I'm ready to go. And to prove that this device is, in the old days, as you said, we used to have fuses. And believe me, I've had trash cans full of these things as I've made mistakes, throw them away, make a mistake, throw them away. Sometimes it was quicker
too. You'd be like, ah!
Yeah, I didn't pay for them, but honest to God, sometimes it was quicker to make a mistake and throw it away than it was to simulate it, it seemed like. But yeah, somebody just said it'll probably work with wine, the WinCUPL.
I'm sure it will work with wine. It will definitely work with wine.
Right. So now one of the things I can do is I can check to see if the device is blank. And you don't see the result, but it said, it's a blank device. So that's cool. I can erase the device, so I'm going to go up here to erase. You can't see it, but I just told it erase the device, and it said, I erased it, which is very cool. It just saved me from throwing that in the trash. And now I'm going to do, I'm going to go up to here to where it says program. Yeah. I'm going to program the device. This would be a lot more, and it shows you how to put it in the ZIF. Oh, you know what? Let me show you the screen here real quick. I'll probably screw up then.
Yeah, I like this. This software is actually not bad for this. It gives you the preview which end of the ZIF you need to put it in.
Right. And there's an important part here, this lock bit. If I were to click the lock bit, that does two things. It keeps it so somebody can't reverse engineer your PAL easily. They would have to run an external state machine. They can't just and stimulate all the inputs and create a vector table for what the chip does, basically de-black box it. Yeah. But it also makes it, I believe, so you can't erase it. So before I program it, I say, yes, I'm going to program it, but I'm not going to set this lock bit right here.
Yeah.
And then I hit program. And it actually works. And that to me was amazing. Now, I had chosen the wrong part originally. I had chosen an ATF16V8C. No, I was just being lazy. I said, it's a 16V8. It'll work. And it got halfway through and said, nope, I blew it. Nope. And I researched it and I chose the right device, ATF16V8BQL, which is
Yep.
the actual device, and then it worked. So you can't be sloppy about which part you put. And that's where the problem with this older programmer was. This older one did lots and lots of the family, just none that I could get. It did gals. I can't buy a gal, not a true gal these days, right? Gal means, it used to mean germanium array logic or something like that.
Generic.
I forget what the
generic
yeah.
array logic. Yeah.
Yeah, I just remember it was like, it was cranky.
Yeah.
But it was cool stuff. So, but I couldn't do this because I couldn't actually get an ATF16V8 BQL in the software for this one. So maybe new software, I don't know, but that's what this Plus did for me.
Firmware updatable, I would have thought.
Well, it firmware updated this week, and I was nervous as hell because I'm like, I'm going to ruin it. But no, the firmware update went okay. So it actually acted like a real device.
How do we check your part now? How do we check the actual part that it's... Do you have a board you can plug it in and...
I do, but I'm not ready to plug it in. But what I can do is I can verify it. Let's see if I can find the... So I come over here and I can verify it against the file. You can't see the screen that just came up, but it's given me the option to verify, and I'm going to click verify. And it says, yes, however you did it, we agree that we programmed it like you told us to.
Yeah, yeah.
All right.
Very cool.
So that's from beginning to end, a real simple little PLD project here. And here's my tube of parts proving you can get them.
Yeah, we need an update. Once you've got that going in the 6502, it's actually, what is that board? It's a mini. You were helping someone in the Discord out with I think it was Frank. You were helping out with a mini. No, I'm getting projects confused here. Someone's doing a mini C128, but that's not this, is it? This is just
no. This is something I did to actually prove that I have an ICE that works. So I needed something to plug the ICE into. And the reason why I was doing an ICE like that is because I have a 32 megahertz 6502 I wanted to run.
Yeah,
so
now that's the one you did that's based on a Xilinx FPGA,
on this.
Is that correct?
No, this is a Cyclone 4.
Oh, Cyclone.
And it's based, it's based on a part you can get from Arrow. Actually, Frank Buss knows these guys. Alan chipped in and said GAL probably means gate array logic, and he's probably right. But this is a Max 1000. This is based on a Max 5 part. And then the other one this is a CYC 1000. So that's the Cyclone 1000. This is by trends.org, TRENZ.org. See if I can get it there.
So it's just like a neat little compute module. And,
it is. Saved me from having to do it. Yeah, absolutely.
Nice. How much are those?
I can't remember. I'm going to say 10 to 20, so not cheap.
Really?
But
I think that's very cheap for something with a Cyclone FPGA on it.
Yeah, you figure half the price is probably the Cyclone. And there's a lot on there because it's got to be programmable and whatnot. So, and what I did was I did a board, and we've talked about this before, that underneath the part, I've got my line buffers and whatnot.
Yeah.
Yes. So, things that were strictly inputs, I forget, there's 5-volt tolerance, but then there's when you actually have to do level shifters. So this is this card that sticks in between it and turns it into a 6502 footprint. Because the pinout's not a 6502.
Of course.
So this was meant to plug into this, and then this was meant to be an ICE to troubleshoot it.
Very cool. And the other one, I think the other one is a Teensy, right? So it's
that's a Teensy 3.5, which happens to be 5-volt tolerant. So you can't use the later ones. I had to use a Teensy 3.5.
Right. My understanding is that Teensy 4s are based on some bigger, more powerful Freescale ARM Cortex M7 or something crazy fast, right? And the Teensy 3.5 is probably a Kinetis sort of family ARM device from Freescale, I believe. Yeah.
Yeah, I forget the The actual stats, I thought it was like 4 meg or so. So you might ask, well, what good's a 32 meg 6502 in a 1 meg board? And the answer is, I mapped memory to the memory that's on this device. Let me do it up here. There's memory on this device, right?
Yeah.
So
yeah.
I mapped fast memory. I created fast memory down at 0 page. And so basically I was going to time the loops and prove that when I'm running out of memory on here, it's very fast, and then it can drop down and run memory on the bigger board at 1 megahertz. And you should actually be able to make software loops and time it and prove that it's 32 times as fast.
Yeah.
So
there's a lot you can do putting a modern heavy-hitting high horsepower device into an old system. You keep running the old system the way it's meant to run and the way you've always liked, but you can do about 400 other things between each main system cycle.
Right. Now, the reason I was doing all this is before the pandemic, Bill Mensch was going to talk at VCF, and myself and Eric Scheffler were going to interview him. We ended up doing it as a virtual interview, but I wanted to bring a 32 megahertz thing to the game. And I was talking with Alexander, who goes by the handle Z. He has the Cactus 6502, and this was meant to plug into his Cactus. And we were going to do that thing where we do loops. And that if this can plug into a Cactus, it'd prove it's 6502 compatible. By the way, I did not write the 6502 core. I am not good enough these days to sit down and just scribble one out without lots of troubleshooting. So I went to opencores.org.
Oh, I love that site.
Picked through multiple 6502s, and I got one that was cycle accurate.
Stuff there, but there's a few gems. You know, there's
That's
diamonds
right.
in the
That's
rough,
right.
and there's true cut gems. You know.
Right. So there's 6502s where somebody just made the equations, but then there are cycle accurate 6502s where they actually recreated the thought process of a 6502. And I think even some of them do the illegal codes correctly and stuff like that. So So that was the idea behind all this. And then the pandemic happened, and I quite simply forgot where I was in the project. I wasn't taking notes because my memory still worked back then, and now it's like I've forgotten where I was, and I kind of lost interest in it. So maybe we'll get interest back here. Anyways, I'm shipping this out to Frank to see if he wants to write some software for it to include the vacuum fluorescent display that we did a while back. But I'm interested to see if he can get the ice to work and everything.
Yeah, that will be cool to see. We'll have to have him on the show and give us a run through once it's all up and running.
Yeah, he's in Germany, but hopefully the time zones overlap, and who knows what internet connectivity, Skype may or may not work. We'll have to find out.
Cool. Well, that's all really fascinating, and I love it. And I just wanted to circle this back to, like, this is there's utility to all this. These devices are still available, cheap, very useful, and often quite enough for a lot of different tasks. And then we go as far as CPLDs, complex PLDs, which are just an evolution of these, right? So if you I don't know if you bring up the data sheet again, you look at those product terms go into an output. Each one of those blocks is no, I forget if it's the whole chip. I think it's not the whole chip. I think it's each output is called with its bank of connections is called a macro cell, right?
Right.
Is that right? And
that's
yes. A PAL V8, the 8 means you've got 8 outputs. PAL 16 V8 means 16 inputs, 8 outputs. But because you've got 8 outputs, you've got 8 macro cells. And compare that to an Altera Max 1000. What does a Max 1000 have in it? Do you have a data sheet handy we could look at? Or we could bring it up real quick.
I want to say, I don't want to guess. What was it, a Max 5? I did know the Cyclones, they had like 16,000 logic array blocks.
That Trends board is using an Altera Max CPLD, correct? It's a Max 1000.
Actually, no, this is a Cyclone 4 in this one. I just
Oh,
happen to
okay.
have a Max also, and the Max is probably a Max 5, I want to say.
Okay.
They
So,
call it a Max 1000, but it's... So,
okay. Yeah,
yeah.
I've got a Max 5 board somewhere, or maybe it's a bit older than that. It might be a 4, version 4. It's up in the
Hey,
cupboard.
if somebody wants to look it up real quick, Frank, if somebody wants to look up what's in a Trends 1000 Max 1000, a Trends Max 1000, it tells the number of, and they call them LE, logic elements, I think, or how would they refer to the
So
macro cells?
Logic Elements is the Xilinx. It's the static RAM FPGA language for the equivalent, but they're different architecturally. So
Yes.
in PLAs, PLDs, GALs, and CPLDs, we're talking about product terms where you have
Right.
wire ORs ANDed together or ANDs ORed
And
together.
they're actually done with lookup tables in the FPGAs. It's actually just a ROM,
it's tons
and
of
it's just
static
terms.
RAM. It's static RAM, and you have an address,
not ROM,
which
but
is your
right.
input, and your I/O it's an input in that it's configurable, and then while it's powered up, it retains the bit pattern inside, and then the outputs depend on the address input to that RAM cell. So they're fundamentally different in how they operate. They use a lot more power, tons more power, because the static RAM uses a lot of power, right?
So Frank just replied that the Max 10, which is correct, it's a Max 10, has
10, that's one.
So 8,000 logic elements.
So they're calling that an FPGA now. Maybe the Altera Max family got so big they switched over to maybe under the hood. You never really know. Like it might be.
I call it a CPLD though. It's actually doesn't reprogram. I mean, you can burn these. I think, like it doesn't need a power. It doesn't need flash. Is my memory about the Max family.
So see that's how it was. They were PLDs that used product terms and electrically erasable or flash-based, floating gate technology. And I think they've gotten just to be so dense, and that I think some of those devices they've just switched to RAM-based FPGA under the hood with a built-in flash for programming them on power up.
Right.
And they just call it, instant on, even though it isn't really. It still takes a millisecond or so to program the whole thing. So
somebody asked, is the 32 megahertz 6502, can it pause like a 65 CO2? And the answer is yes, it can. But the secret is it's not really pausing. There's a 160 megahertz clock, if I remember right, and 32 meg was a division of that. And so that real fast clock is running the whole time, but I'm monitoring the clock that I get from the main board. And so if it clocks, I go ahead and do my thing. If it pauses, I'm just sitting here with the master oscillator, but the state machine is paused. So yes, I can go as fast or as slow as whatever clock is given to me. And if the clock is changing frequency, so can I. Because I'm just basically, when I get a phi rising edge, I do all my computation. The clock falls, I do all the computation, and I do it in 1/32nd the time that a normal 6502 takes.
Right, but based on what you just said, you could, if you wanted, you could do it in 168th of the time.
No, because it takes about 8 or 9 cycles to simulate all that internal logic. So you really do need to pipeline your way through to do it.
Right.
So yeah, it'd be nice if I could have a 128 term input. Maybe I could, instead of 5. So. All right, we're coming up on 5 minutes till the. Hey, do you have an update for us on the project you've been working on?
Oh, I don't. I just realized I do not have Fusion open right now. But if you
opened it, it'd probably crap your Skype.
Yeah, it might briefly. I'm just opening it up, but it took me months and months and months of, half an hour here, 20 minutes there, to actually do the engineering and get the schematics done, because I had to make all the parts in the library. I prefer to do that. There were hundreds of thousands of parts in the library to begin with, but I like to create my own library for the first project just to get to really know the workflow.
Right.
I
did
and
say.
a lot of the parts I wanted to make aren't even for this project. So anyway, but so I finally got to almost completion, and this week I started routing the board since our last Friday, and within a few hours I had it almost completely routed. I was blown away with how good the routing tools are already in Fusion. So I had a really easy time doing that. It's going to be a 4-layer board just because I want good signal integrity. So I've got plain layers on the inner 2 layers. And then, is it open yet? It's open. So I could probably share my screen. Let's see. Let's see.
And the smell of burning smoke.
Yeah. I don't know if you can see this. I see that you're getting the Skype logo instead of the application.
Hang on. I'll try and get the application up. Give me a second. All right. I have your screen up. I don't know where you can see it or not.
Yeah, I'm just opening up the project here. I need to come up with a name, and this is something I wanted to bring up too on the channel and the Discord, maybe get everyone to contribute. So I'm going to soon create a formal document that explains what the heck this thing is. It's just a general purpose compute board. It's got an ESP32, you can see that there in the preview, an ESP32, and I'm calling it an FPGA, but really it's a CPLD. It's a Lattice Mark XO2. This device is the biggest one in a hand solderable footprint. It's about a $17, $18 in quantity of one part. So it's not the cheapest. It wouldn't be the cheapest board to build, but it's got a lot of power. So I've almost completed the routing, but I discovered I was looking at reference designs. And there's 2 reference designs for this part. One is this breakout board, which
right.
I don't know if you can see that. I'm holding it up to my camera.
Yeah, I've only got the shared screen up right now.
There's the Lattice breakout board, and that one I noticed in the schematics. So if I go back to the schematics, I modified the schematics a bit through the week because I got a little confused over the power supply requirements, because one reference design that uses this part has a chip that has this, and I realized there's 2 variants of this FPGA that have different power supply requirements. One uses a core voltage that can be 2.5 to 3.3 volts.
Right.
And the one on the breakout board has a core voltage. The schematic of the breakout board has the core voltage at 1.2 volts.
Yeah, we're losing you. Hey, can you disconnect your camera and reconnect to get rid of the Skype logo? All right. We're waiting for... So while we do that, I'm going to show what we're going to show next week is this pretty thing. Alan, you may recognize this. And as a matter of fact, Alan, I have a question for you. How do I manipulate the position of the bus on the screen? I can position all these different traces, but when I include a bus with analog traces, and this is really cool how I can do this logic here. For a trigger, and I wanted to show that, where I can pick the different signals. That's a mixture of analog and digital, but once I do that, I can't change where this purple thing is on the screen, so I'd love to know how. So we'll be showing this next week. This is from a Commodore 128. Somebody had asked me a question about when it goes into double speed mode and comes out of it, and so I threw it on my Tektronix scope and combined analog probes and digital and came up with a cool trace. So, Ben, are you back with us?
I
All right.
think I am. I don't know what.
Okay, I can hear you
so
now. Can you
Skype right
disconnect
now.
your camera and reconnect it to try and get rid of the blue? I've lost you again, I think. So we're at the end of the hour here anyway, so that was a glimpse of what we'll be doing next week. And we're going to give...
Yeah.
There you are. I can hear you a little bit.
Yeah, I turned my camera off. I'm just so annoyed with Skype. But anyway, yeah, we are out of time. I'll describe the changes next week because by then I'll have completely finished. There's still a couple of things I want to add to this. I want to put a rotary encoder on it, but this is the current state. It's almost completely routed.
Cool.
And this is the 3D view.
I love it.
It's coming along nice. I have an assembly too that shows the LCD panel on the backside with the ribbon connectors coming over a bit. I'm still working on tidying up the silk screen and putting all the reference designators where they're going to be clearly visible.
Right. Yes, the old... I wish... There's DRCs for a lot of things, but I wish there was one that would just jiggle the reference designators into where they can be seen where they're not on bare copper or overlapping a component.
Hey,
I wish there was automation for that.
That's a brilliant idea. Push and shove for silk screen.
Yeah, and just write a rule that says silk screen can't go over copper route, and let it go.
Yeah, because the rules are there and they'll be checked against did you pass, did you fail, but it won't move it for you or help you position it. And that's actually where it would get more interesting and more helpful. I agree.
Yeah, even if it only checked one of the, if you figured a cell around it and it said, well, I tried diagonal up, to the left, I tried up, I tried diagonal up to the right, and none work. That'd be better than manually doing 400 components, in my humble opinion.
Yeah, totally. Cool, man.
All right.
Well, it's been a pleasure, and thank you for giving us that detailed walkthrough programming a
PLD. Yeah.
Yeah. What's the part number again? It's a ATF16V8BQ something.
BLQ something like that. Yeah.
It's
so it's in the Discord. I put links in the Discord to the part itself along with the 22V10. I put a link to WinCUPL and I put a link to the programmer itself. So if you want to get into PLDs, it's all right there in our Discord channel. Yep. Again, to find our Discord invite, go to Coriolis-effect.com and you'll see a link. It's right on the menu for Discord invite from there.
One last question I have for you on those.
There you are. You're back.
Yeah. One last question. Are they only 5 volts? Do they work at 3.3? The one that you're using works at 5, I would assume.
The one I'm using works at 5. I'll admit I don't know, and I'll have to go into... That's an interesting question. I don't know if they have 3-volt versions of these, but I will have to check.
Yeah.
So cool. I'll write that down for next week.
Awesome.
Excellent, Ben. And my friend, it was great chatting with you. Great to see an update on your project, and we'll have to get more into that too. And while you were out, I was showing my Tektronix screen from the C128. We'll have to talk about that a little bit next week as well.
Yeah, well, you mean the mini C128, right?
Actually, it's off my regular one in the back.
Oh, okay.
The people that were doing the mini asked me a question about how the real hardware works. So for the second time in 35 years, I hooked scopes to a 128. And like I said, I combined analog and digital probes to create an address decode along with the clocks and the chip selects, and was able to go into a menu and say, this one's high, that one's low, this one here, and add them all together to create my trigger event, which was cool. Very cool. So, all right, we will see you